All right, so in this video, we're going to do a brief introduction to simple harmonic motion. It turns out in this course, we don't do as much as what's in the textbook. We're only going to talk about a mass that's tied to a spring and it's allowed to oscillate back and forth freely. So that's what I want you to picture. As you see in my beautifully drawn picture here, that's a spring with a weight attached to it. And I want you to picture what's going to happen if you hang a spring and then attach a weight. It's going to bob up and down for a while until it rests at what we like to call equilibrium. So when that weight is at rest, or when you put it at rest, we call that equilibrium. So if I set that into motion again, the weight is just going to bob back and forth. It's going to hit a high point, then a low point, then another high point, then a low point. It's going to keep coming back to that same high and low point under the assumption that there's no other resistance acting on the object. So this is more or less what's happening here, the steps 1, 2, and 3 that I just went through. So we call S of t the displacement, kind of like distance, except it's allowed to be negative, okay, relative to equilibrium. So if S of t is positive, that means that the object is, or the weight is above equilibrium. If S of t is less than 0, then it's below equilibrium. And if S of t is equal to 0, the object is at the equilibrium position. Okay, so what we have is a model for the displacement of the object. And it shouldn't be a surprise that it is a trigonometric function. So we are going to talk about those that start at its highest point from equilibrium and then oscillate from there, or lowest point as it turns out. So S of t is equal to a cosine, that is the Greek letter omega t. So t is going to be the number of seconds that have passed. A is the amplitude. Actually, if you really want to get technical, the absolute value of A is amplitude, because we could talk about a negative A. And that's going to be determined by the width of the spring. A heavy spring is not going to bounce back and forth too much. A very light spring, kind of like a slinky, is going to bounce back and forth pretty freely, okay? So it's probably going to go further up and down. Now, the period, as we already know from earlier, is 2 pi divided by whatever the number is in front of t. So that's 2 pi over omega. And we can define what's called the frequency, which is basically the reciprocal of the period. So let's say the period is 2 seconds. That means that every 2 seconds we go through one cycle or one revolution, okay? That means the frequency is 1/2 a period every second. So the frequency is telling us how far we go every second. So frequency is the reciprocal of period. So that's this formula right here. Notice how those are just flips of each other. Okay, so in the graph, here's what we're basically looking at. So I took A to be positive. One period, remember, is the distance, the time interval between two maximum points or two minimum points. Okay, and the frequency is, again, the reciprocal of that quantity. So let's look at an example of how we can pull this information together. Here we have a general S of t. We want it to be a cosine omega t. We are told that its initial position is 5 inches, and that's 5 inches above equilibrium. So we are going to assume that this is measured in inches. And the period is 1.5 seconds, which means it repeats itself every 1.5 seconds. Every 1.5 seconds, it returns to its high point. Every 1.5 seconds, it's going to return to its low point. Then we're going to figure out what S of 1 is, and then we're going to try to answer the question, is the weight rising or falling? So let's look at the first part. We're given that S of 0 is 5 inches. So let's see. S of 0 is a cosine 0, which is 5. Now we know that cosine of 0 is 1, so that means A is equal to 5. Yay. So that means S of t is equal to 5 cosine something t. Now, we know that the period is 1.5, so we know that the period is 2 pi over omega, and that's equal to, now I could write 1.5, but I'm going to write it as 3/2. And I'm going to now solve for omega. So this means that 3 omega is equal to 4 pi, cross multiply basically. And then that means omega is 4 pi over 3. So there is the model for our harmonic motion. Okay, so now we can answer almost any question using that equation. We want to know what S of 1 is, so just changing color here. S of 1 is going to be 5 cosine 4 pi over 3. Now, cosine 4 pi over 3, you could get that out of your calculator if you want to. That is one of our special angles. That's a reference angle of pi over 3, or 60 degrees in the third quadrant. So we know that cosine is negative. In fact, it's negative 1/2. This is 5 times negative 1/2, which is negative 5/2, which means it is below equilibrium after 1 second. Okay? And then what we want to know is the weight rising or falling after 1 second? Well, that's going to be best answered by looking at the graph of the harmonic motion. So I do have a picture here with some things labeled. So the period, as we said before, was 1.5 seconds, which is right here. And kind of just gauging where 1 second is. Well, we know that halfway between the maximum points, we have a minimum point. So we know that the minimum occurs when t equals 0.75, halfway between 0 and 1.5. And we also know that halfway between the min and the max is one of the x-intercepts, or in our case, the equilibrium point. That's going to be 1.25 seconds. So we know that t equals 1 is somewhere between 0.75 and 1.25, which means it's right here, which means that the object is rising when t equals 1 second. And these are the kind of things we can analyze with harmonic motion. Thank you for watching.